When you gaze upon the night sky, you are greeted by an expanse that feels limitless, tranquil, and filled with enigma. The Milky Way arcs overhead like a celestial river of light, with every star holding the potential to be the heart of its own system, orbited by planets that could be much like your own Earth. The planets you recognize are situated within the solar system, held in place by the Sun's powerful gravitational influence. This enormous, middle-aged thermonuclear star keeps all these cosmic bodies in their predictable paths. A total of 8 planets circle it, from the compact, rocky Mercury to the distant gas giant Neptune, which marks the far reaches of your planetary neighborhood. Each planet is defined by a distinct atmosphere, climate, and geological timeline, presenting scientists with a unique lens through which to observe processes that have been developing over billions of years. For instance, Mercury, the planet nearest to the Sun, features a surface scarred by craters, closely resembling your moon. Its temperatures swing dramatically, soaring above 400 degrees Celsius during the day, before falling to nearly -150 degrees Celsius at night, creating an ideal laboratory for studying how rocks and minerals react to extreme thermal stress. Venus, the second planet in line from the Sun, is frequently referred to as Earth's twin because of their comparable size and mass. Yet its surface is concealed beneath dense clouds of sulfuric acid, and its atmospheric pressure is 100 times greater than what you experience on Earth. Ferocious winds gusting over 100 kilometers per hour sweep its landscape, where temperatures remain consistently above 460 degrees Celsius, offering a case study for the greenhouse effect under extreme circumstances. Earth, positioned as the third planet, is remarkable for its abundant liquid water, an atmosphere rich in oxygen, and an incredible diversity of life. The tilt of your planet's axis is what gives you seasons, while its magnetic field and atmosphere work in tandem to protect you from harmful solar radiation and cosmic particles. This finely tuned equilibrium makes Earth a special sanctuary for life, motivating the scientific pursuit of similar conditions on exoplanets, worlds orbiting stars far beyond your own. Mars, the fourth planet, continues to fascinate scientists with its frigid climate and prominent polar ice caps. The planet's signature reddish color is due to iron oxide, and its very thin atmosphere consists mainly of carbon dioxide. Robotic rovers and space missions have uncovered evidence of ancient water and formations resembling riverbeds, hinting at a much warmer and wetter past. Consequently, Mars is frequently seen as a prime candidate for future human settlement, making it a major focus of research. Jupiter, the fifth planet, is a colossal gas giant dominated by an enormous atmosphere of hydrogen and helium. Its most recognizable feature, the Great Red Spot, is a gigantic storm system that has been churning for more than 300 years. Jupiter is also accompanied by a system of over 80 moons, including the notable Io, Europa, Ganymede, and Callisto, which display incredible geological activity and hide subsurface oceans, aiding our comprehension of gas giant dynamics. Saturn is celebrated for its spectacular rings, which are composed of countless particles of ice and rock that form an unparalleled structure both visually and physically. While Saturn's mass is approximately 9 times that of Earth, its overall density is so low that it would float in water, assuming a body of water large enough could exist. These rings are more than just a beautiful sight. They provide a natural laboratory for observing the dynamics of small celestial bodies and the accretion processes that build planets and moons. Uranus and Neptune, the solar system's ice giants, occupy its most distant regions. The methane in their atmospheres imparts a distinct blue coloration, while their interiors are thought to be made of icy and rocky cores. These planets spin at extreme angles, almost on their sides, which leads to bizarre climatic patterns and magnetic fields. Investigating their orbits and fields helps scientists decipher the mechanisms of planetary system formation at vast distances from a central star. Exoplanets, which are worlds discovered outside of your solar system, are astonishing in their variety and strangeness. Since the early 2000s, thousands of these planets have been identified by scientists employing techniques like transit methods, radial velocity measurements, and direct observation. Some are located in the habitable zone, a region where conditions could potentially support liquid water. This diverse population includes super-Earths, hot Jupiters, and planets orbiting perilously close to their stars. The existence of exoplanets is fundamentally tied to the life cycles of stars and the dynamics of vast gas and dust clouds within galaxies. The accretion process within protoplanetary disks, the birthplace of planets, can unfold over millions of years, leading to the formation of celestial bodies with a wide range of masses, compositions, and orbital paths. Data from space telescopes like Kepler and TESS, along with ground-based observatories, has allowed for the creation of the first extensive catalogs of these distant planets. We are now on the verge of grasping the universe as a dynamic, evolving system, where every planet is a unique world governed by its own history and physical laws. The investigation of planets and exoplanets not only uncovers the physics and chemistry of these remote worlds, but also raises deep philosophical questions. You are prompted to wonder how widespread life might be, how planetary systems truly come into being, and whether other civilizations could exist somewhere beyond Earth. When you observe the night sky, you see points of light that seem steady and everlasting. Yet any one of them could be a star with a whole system of planets in its orbit. These exoplanets have rapidly emerged as one of the most compelling areas of study in contemporary astronomy. The very first verified detections of these worlds occurred in the 1990s, before which their discovery was deemed nearly impossible due to immense distances and their faint reflected light. It was through breakthroughs in radial velocity and transit observation technologies that scientists finally became able to detect their subtle effects on the stars they circle. A tiny, almost imperceptible wobble in a star's spectral lines can signal the presence of a massive orbiting companion. The transit method, however, truly transformed the field of exoplanet hunting by monitoring a star's brightness for the slight dip that occurs when a planet crosses in front of it. Using high-precision photometers to detect these subtle changes in light, astronomers have identified thousands of distant worlds, including hot Jupiters, enormous gas planets that complete an entire orbit around their stars in just a matter of days. Directly imaging an exoplanet presents a much greater technical hurdle, but the scientific rewards are immense. Because these planets produce or reflect only a faint amount of light, they must be teased out from the overwhelming glare of their parent stars with specialized telescopes equipped with coronagraphs and interferometric systems. Such direct observations enable scientists to probe the atmospheric makeup, spectral signatures, and even the weather systems of these alien worlds. For instance, finding traces of water vapor or methane provides powerful clues about a planet's potential habitability and its ongoing chemical processes. Measurements using the radial velocity technique provide essential information regarding an exoplanet's mass and orbital path. The gravitational pull from an orbiting planet causes its star to move slightly, inducing periodic shifts in its spectral lines through the Doppler effect. Incredibly, even oscillations as small as a few meters per second can be registered by today's advanced instruments, which has made it possible to find planets with masses similar to Earth's orbiting close to their stars. Exoplanets are categorized based on their size, mass, and overall composition, revealing a diverse celestial zoo. You have super-Earths, which are larger than our own planet yet maintain a solid surface, and mini-Neptunes, which are defined by their thick, gaseous atmospheres. Hot Jupiters are gas giants that orbit precariously close to their stars, whereas their counterparts, the cold gas giants, circle at immense distances, sometimes many tens of times farther out than Neptune. Among the most compelling discoveries are multi-planet systems that exist in a state of resonance, where their orbital periods are perfectly synchronized in a way that ensures the system's long-term stability. You can see examples of this cosmic harmony in the Kepler system, where the regular transits of several planets create an intricate rhythmic dance. The atmospheres of these distant worlds are examined using spectroscopy, a method that involves analyzing the light that filters through a planet's atmosphere as it passes in front of its star. This technique allows scientists to determine the composition of gases and identify compounds that could signify biological activity. Specifically, the combined detection of oxygen, ozone, water, and methane could act as a strong indicator for the potential presence of life on a faraway planet. Every exoplanet that is found deepens our knowledge of how planetary systems are born and develop. By drawing comparisons to our own solar system, astronomers can refine their models of gas and dust disk evolution, the creation of giant planets, planetary migration, and the orbital resonances that give systems their stability. These increasingly sophisticated models help us predict where undiscovered planets, including potentially habitable ones, might be hiding. The latest generation of observatories, such as the James Webb Space Telescope, along with future missions, are poised to dramatically expand our capacity to investigate exoplanets. These powerful tools will not only discover new worlds, but will also analyze their thermal emissions, cloud formations, weather patterns, and perhaps even their seasonal changes. This ushers in an era where we can create detailed maps of planets, their atmospheres, and their chemical makeup, a feat that once seemed entirely out of reach. The study of exoplanets is profoundly altering our view of the universe. Worlds that you might have previously considered mere fantasy are now the focus of serious scientific inquiry. We are learning that the variety of planets is staggering, ranging from rocky Earth-like bodies to gas and ice giants that follow unique trajectories around their stars. This growing understanding prompts us to contemplate not only the physics and chemistry of these worlds, but also the possible forms life might take, the long-term future of humanity, and the breathtaking complexity of the cosmos itself. When you delve into the topic of exoplanets, it is essential to highlight some of the most impressive and well-known discoveries that have become symbols in the search for worlds beyond our solar system. Each of these planets exhibits unique properties, charting new territory for researchers, and encouraging all of us to envision what these places might truly be like if we could ever travel to them. One of the earliest and most celebrated exoplanets is 51 Pegasi b, which was identified in 1995. This world is a quintessential hot Jupiter, a colossal gas planet orbiting incredibly close to its star, with a mass about half that of our own Jupiter and an orbital period of only 4 days. Its discovery was a watershed moment, as it defied the prevailing models of planet formation, which held that giant planets could only form far from their stars in colder regions, where gas and dust could readily accumulate. Another groundbreaking discovery from the 21st century is the TRAPPIST-1 system. Located in the constellation Aquarius, it contains 7 planets orbiting a dwarf star. Remarkably, all of these planets are comparable in size to Earth, and 3 of them are situated within the habitable zone, where surface temperatures might permit the existence of liquid water. This finding ignited intense scientific and public fascination, as it was the first system found to host multiple potentially habitable worlds close enough to one another that we can theoretically study their interactions. Proxima Centauri b stands as another compelling case. This exoplanet orbits Proxima Centauri, the star closest to our Sun, at a distance of just 4 light-years. With a mass approximately 1.5 times that of Earth, it is also positioned within its star's habitable zone. Scientists are actively using spectroscopic analysis and space telescope observations to investigate its atmosphere and the potential for water. Although the conditions on this planet are still a matter of speculation, finding a potentially habitable exoplanet so near to us invigorates concepts for future interstellar journeys. Kepler 186f represents yet another pivotal discovery. Uncovered by the Kepler telescope while observing the constellation Cygnus, this planet is similar in size to Earth and also orbits within the habitable zone. These characteristics make it one of the strongest contenders for possessing the necessary conditions to sustain life, further fueling our quest to find another world like our own. I think the discovery of Kepler 186f is truly significant, because it shows you that planets capable of supporting liquid water can exist even around small red dwarf stars. This discovery dramatically broadens the horizons for where we might search for life beyond our own solar system. Then you have systems like Kepler 90, which are astonishing in their intricacy, hosting 8 planets, a number directly comparable to our own solar system. The sheer variety in the sizes and orbits of these worlds creates a complex dance of gravitational forces. Discoveries of this nature are invaluable, as they provide us with the data needed to model the long-term stability and evolution of planetary systems and, ultimately, to estimate the probability of habitable worlds forming elsewhere. One of the most fascinating parts of exoplanet research for me is their incredible diversity. You find planets in extreme orbits, circling not 1 but 2 or even 3 stars. These are what we call circumbinary planets. A classic example is Kepler 16b, a gas giant similar to Saturn that orbits a pair of stars, showcasing just how complex and strange orbital mechanics can be, and highlighting their profound impact on a world's climate and atmosphere. You'll also find exoplanets that are shocking in their closeness to their parent stars. Consider the hot Jupiters, which orbit so tightly that their temperatures can surpass 1,000 degrees Celsius, far hotter and closer than Mercury is to our Sun. These worlds, with their fierce winds and unique atmospheric chemistry under intense radiation, serve as perfect extreme laboratories, helping us grasp the dynamics of gas giants, including atmospheric circulation and heat distribution. In stark contrast, you can look to the ice giants located far from their stars, which offer a window into frigid atmospheres, the behavior of methane clouds, and the accretion processes that give rise to moons. By studying these distant, cold worlds, we can fill in the missing pieces and achieve a more complete picture of the incredible variety found in planetary systems across the galaxy. With every new exoplanet we identify, you can see us taking another step toward comprehending the universe's immense variety. We're uncovering a catalog of worlds, rocky and gaseous, scorching and frozen, orbiting alone or within intricate systems. This ever-expanding knowledge not only broadens our concept of what's possible, but also fires our imagination about the potential forms of life and the powerful cosmic forces at play on these faraway planets. Now, when I talk about planets orbiting other stars, I believe it's impossible to ignore one of the most exciting fields of study: their atmospheres. You see, a planet's atmosphere is so much more than a simple layer of gas. It's a dynamic system that dictates everything from climate and weather to chemical makeup and, crucially, its potential to support life. By analyzing these atmospheres, we can move past simply knowing a planet exists and begin to visualize what it would actually be like to be there. A technique called transit spectroscopy has truly transformed how we study these alien skies. When you watch a planet cross in front of its star, a tiny fraction of the starlight passes through its atmosphere. Because different chemical elements absorb light at very specific wavelengths, they leave a unique spectral signature that we can analyze. This allows us to identify the gases present, detect clouds, and even infer chemical reactions, leading to the first confirmed findings of water vapor, methane, and carbon dioxide on distant worlds. With spectroscopy, you're able to identify not just the main atmospheric components, but also trace amounts of rarer elements. For example, the distinct spectral lines of sodium and potassium can tell us about the structure of a planet's upper atmosphere. The detection of more complex molecules, like ammonia, ozone, or organic compounds, offers even deeper clues into a world's chemical history and its potential for hosting life. I should also mention another vital technique: the direct imaging of exoplanets. Using advanced telescopes outfitted with coronagraphs, we can block out the overwhelming glare of a star to capture the faint light a planet reflects or emits. This allows you to directly measure its temperature, spot cloud formations, and even observe weather patterns like winds and massive storms. Sometimes, we can even detect seasonal shifts, making these distant worlds feel incredibly dynamic and alive in your mind. We also rely on infrared spectra to investigate a planet's thermal radiation. A planet doesn't produce its own light, so by analyzing the infrared heat it gives off, you can measure its surface temperature and assess its overall energy balance. This technique reveals atmospheric layers that are otherwise hidden from view and is fundamental to understanding how heat moves around a planet and drives its climate. A truly critical part of this entire endeavor is the hunt for biomarkers, which are specific chemical compounds that could signal the existence of life. You'd be looking for substances like oxygen, ozone, methane, and water, but it's their combined presence that is especially compelling, since here on Earth, this particular mix is a product of biological processes. Finding an exoplanet with these chemical fingerprints would be a monumental first step in the search for life elsewhere in the cosmos. Today's space missions, particularly the James Webb Space Telescope, have given us an unprecedented ability to probe exoplanetary atmospheres. With its highly sensitive infrared instruments, you can capture the faint thermal glow from these distant worlds, allowing us to build incredibly detailed atmospheric models. This information is then used to forecast weather, determine chemical makeups, and even simulate the behavior of complex cloud systems on these alien planets. You have to remember that exoplanet atmospheres are incredibly varied. On a hot Jupiter, you'll find dense, superheated layers with winds gusting at thousands of kilometers per hour. Conversely, the atmosphere of an ice giant is a frigid mix of methane and ammonia, creating clouds and storms completely alien to our experience. This vast range of conditions provides us with priceless data on planetary formation and helps us determine which atmospheric phenomena are common throughout the universe and which are unique. Ultimately, I want you to understand that studying the atmospheres of exoplanets goes far beyond merely analyzing a list of gases. It's about piecing together the complete story of these distant worlds, understanding the intricate systems that govern them, and ultimately, gaining a deeper perspective on our own place within the cosmos. Exploring these distant worlds gives us a chance to investigate climatic systems, witness the interplay between stars and planets, trace chemical cycles, and grasp the mechanics of weather. Every new finding moves us closer to understanding the universe's incredible variety and unpredictability, letting us envision what it would be like to stand on these alien surfaces, to see suns setting over strange oceans, or clouds that swirl in the wind, as if choreographed to a cosmic rhythm. When you delve into the subject of planets and exoplanets, you cannot overlook the dynamics of their movement. The orbits of planets are far more than simple paths around their stars. They represent intricate gravitational ballets that define the architecture of an entire system and dictate its climate, seasons, and even a world's potential for hosting life. Each orbital path is the culmination of billions of years of gravitational interactions with other celestial bodies, the constant pull of its star, and the broader cosmic environment. Within our own solar system, the planets follow nearly circular orbits, with only slight deviations that contribute to the system's long-term stability. However, when we look at other star systems, we find an astonishing variety of orbital arrangements. Some planets travel on highly elongated, elliptical paths that swing them incredibly close to their star before sending them far out into the cold. This results in dramatic swings in temperature and light, creating environments that are likely very hostile to life. Orbital resonance presents another captivating element of planetary dynamics. These resonances happen when the orbital periods of neighboring planets align in simple whole number ratios. For instance, if one planet completes exactly 2 orbits in the time it takes another to complete one, their gravitational tugs can stabilize the system and help prevent catastrophic collisions. We can observe such harmonies in the moons of Jupiter and in exoplanetary systems like TRAPPIST-1, where a whole chain of planets is interlocked in resonance. The influence a star exerts on its planets is also immense. Gravitational tidal forces have the power to heat a planet's interior, particularly if its orbit is highly elliptical. This phenomenon, referred to as tidal heating, is a critical driver of volcanic activity, the formation of oceans, and the retention of internal heat. A classic example is Jupiter's moon Io, which is famous for its extreme volcanism, fueled by the tidal stresses from Jupiter's gravity and the rhythmic pull of its neighboring moons. Particularly fascinating are systems that contain multiple stars, where planets are found orbiting in binary or even triple star arrangements. The gravitational forces in these systems are far more complex, allowing planets to either orbit a single star or trace a wide path around the entire stellar group. The planet Kepler-16b, which orbits a pair of stars, is a perfect illustration. Its orbit is stable, but it exists in a delicate equilibrium maintained by the gravitational pull of both its suns. The long-term viability of any planetary system hinges on the mass of its planets, their distances from one another, and their overall spatial configuration. If massive planets are situated too closely, they can disrupt each other's paths, potentially leading to planets being ejected from the system entirely. In contrast, finely tuned orbital resonances can lock a system into a stable arrangement that persists for billions of years, a process that scientists simulate on supercomputers to forecast orbital changes, the formation of rings, and even possible planetary collisions. The creation of planetary systems is a gradual and intricate process that begins with a protoplanetary disk of gas and dust circling a young star. Within this disk, particles collide and stick together, growing into planetesimals and eventually forming full-fledged planets. The inner worlds are usually rocky, whereas giant planets take shape further out where colder temperatures allow for the accretion of vast amounts of gas. Over cosmic timescales, these planetary orbits can shift, migrating closer to or farther from their star and reshaping the system's dynamics. There are also extreme planetary configurations, such as worlds orbiting dangerously close to their star, or icy giants lurking at the very edge of their systems. Some planets are subjected to frequent gravitational disturbances, which can alter their axial tilt and the eccentricity of their orbit. These changes have profound effects on climatic cycles, the nature of seasons, and how heat is distributed across the planet's surface, helping us understand the conditions that might permit liquid water and, by extension, life. In the exoplanetary systems we have discovered, the sheer diversity is breathtaking. We have found everything from compact systems with multiple planets packed tightly together, to sprawling systems with distant giants. We have seen stable, circular orbits as well as eccentric and resonant patterns, confirming that every system is a unique, cosmic creation. These observations are revolutionizing our understanding of planetary dynamics and improving our ability to predict where habitable worlds might be found. To study the orbits, interactions, and motions within planetary systems is to tune into the slow, majestic cadence of the universe. Each movement, each trajectory, and each gravitational pull is a step in a cosmic dance that has been unfolding for billions of years. This dance continues to sculpt unique worlds and unveil the boundless variety of planetary systems that populate our galaxy. When we discuss exoplanets, we are truly talking about an immense spectrum of worlds, each with its own distinct character. These planets can range from colossal spheres of gas and massive rocky bodies to frozen worlds orbiting at the fringe of their stellar systems. Learning about this variety enables astronomers to classify these planets, forecast their climatic conditions, and speculate on their capacity to support life. Among the most striking categories are the hot Jupiters, enormous gas giants that orbit their stars at incredibly close distances, sometimes tens of times nearer than Mercury is to our Sun. On these worlds, temperatures can climb above 1,000 degrees Celsius. Their atmospheres are composed of water vapor, carbon dioxide, and other gases, while ferocious winds whip clouds around the planet at speeds of thousands of kilometers per hour. Though their conditions are extreme, hot Jupiters offer scientists a laboratory for studying atmospheric dynamics and heat transfer under intense light and gravity. Super-Earths represent another class of planets, with masses greater than our own world, but less than that of Neptune. These intriguing planets can be rocky in composition, may possess thick atmospheres, and could even host vast oceans. Their discovery has opened up a whole new frontier in the search for worlds that are fundamentally different from Earth, yet might still harbor the necessary ingredients for life. When you're searching for worlds that could support life, these planets are especially compelling, because so many reside within their star's habitable zone. Super-Earths serve as a powerful example of just how varied the environments on terrestrial planets can become. showing us that their geology and climate can be dramatically different from our own. Another class of exoplanets you'll find are the ice giants, which exist in the cold, distant reaches of their solar systems. Their atmospheres are a mixture of methane, ammonia, hydrogen, and helium, with their actual surfaces concealed by thick cloud layers. Temperatures on these worlds can plummet to dozens of degrees below 0 Celsius, and by studying them, we gain crucial insights into how planets form, how their atmospheres circulate, and how they manage to retain heat so far from their stars. You also encounter truly exotic worlds, like planets girdled by rings similar to Saturn's, or those with highly eccentric orbits that cause them to swing incredibly close to their star before arcing far out into space. Some even circle 2 or 3 suns, resulting in extraordinary patterns of light and unique climate conditions. These strange systems really underscore the immense diversity of the cosmos and the sheer variety of possible planetary arrangements. Researchers are particularly focused on worlds that might offer habitable conditions. You find these planets within what is known as the habitable zone, a region where the temperature is just right for liquid water to persist on the surface. These worlds could possess atmospheres with oxygen, carbon dioxide, and water vapor, alongside vast oceans and continents. Examining them fuels our speculation about potential life forms and drives the hunt for biomarkers, which are the chemical fingerprints that might reveal the existence of organisms. What's fascinating is that some exoplanets display extraordinary climatic events. On worlds known as hot Jupiters, for instance, powerful winds can carry thermal energy from the perpetually sun-baked side to the dark side, generating severe temperature differences. Meanwhile, on ice giants, clouds of ammonia and methane give rise to intricate weather patterns, complete with massive storms and swirling vortices. By observing these phenomena, scientists can build models of atmospheric dynamics that you simply couldn't study otherwise, enabling them to project climate scenarios for many different planetary types. You'll also find that exoplanets span an incredible range of sizes and masses, from rocky bodies tinier than our own planet to colossal giants many times more massive than Jupiter. The size and mass of a world directly shape its gravitational pull, its atmosphere, and its internal processes. More massive planets have the gravity to hold on to thick, dense atmospheres, whereas smaller ones tend to shed their gases, leaving only a thin atmospheric layer. This distinction is critical, as it dictates not just the climate, but also the very possibility of life surviving on the surface. Our ability to observe these distant exoplanets is a testament to advanced telescopes and sophisticated techniques for analyzing starlight. Every single discovery broadens our comprehension of planetary diversity, revealing a universe far more intricate and varied than we ever conceived. We're now learning about worlds with fast or slow orbits, on circular or elongated paths, some shrouded in clouds and others with vast oceans. Each one is a distinct realm, opening up new frontiers and inspiring us to envision the kinds of life or climate systems that could thrive in such places. Exploring this vast assortment of exoplanets makes you realize the cosmos isn't merely an empty void dotted with stars, but an endless kaleidoscope of worlds, each with a unique story, atmosphere, and climate. As we contemplate these discoveries, we inevitably confront one of humanity's most profound questions. Are we alone? The quest for life on other worlds transcends mere scientific inquiry. It's a profound effort to grasp just how special our own planet and existence truly are. With each new mission and technique, It feels as though we are slowly unlocking a door to a universe teeming with cosmic secrets. A central strategy in this search involves looking for biomarkers, which are chemical compounds or elements that could signal the existence of life. Here on Earth, substances like oxygen, ozone, methane, and water are intimately tied to biological processes. Consequently, finding these gases in the atmosphere of a distant planet is a top priority for astronomers. For instance, if you were to discover both oxygen and methane coexisting in an exoplanet's atmosphere, it would be a strong hint that processes similar to biology might be at work. This is where a technique called transit spectroscopy proves invaluable. When a planet crosses in front of its star from our point of view, a fraction of the starlight passes through its atmospheric fringe. Since different gases absorb light at very specific wavelengths, this process imprints a unique spectral signature on the starlight. By analyzing this signature, scientists can identify water vapor, oxygen, carbon dioxide, and other compounds that could be tied to life. And with every new generation of telescopes, the precision of this method improves, bringing the detection of faint biological signs within our reach. An alternative method focuses on analyzing a planet's direct emissions. Using advanced instruments like coronagraphs and infrared detectors, you can effectively block out the overwhelming glare of the parent star, allowing for direct observation of the much fainter planet itself. The light emitted by the planet contains crucial information about its temperature, cloud cover, atmosphere, and potential chemical makeup. This information is then used to model its climate and atmospheric behavior, and even to assess the probability of liquid water on its surface. Of course, identifying planets within the habitable zone remains a cornerstone of this search. This is the orbital region around any given star where conditions are temperate enough for liquid water to potentially exist. While planets found in this zone are considered prime candidates, their location alone is no guarantee of life. For life to emerge and thrive, you also need the right overall conditions, including a stable atmosphere and a chemical environment conducive to biological activity. Looking ahead, upcoming missions are set to dramatically broaden our capabilities in the search for life. The next wave of powerful telescopes, for example, will do more than just find new exoplanets. They will be able to analyze their atmospheres with a level of detail and precision that has never before been possible. These advanced instruments will empower scientists to chart the cloud systems, gauge temperature gradients, and monitor seasonal shifts on distant worlds. The capacity to witness water cycles, storms, and wind patterns will let researchers pinpoint where conditions most closely mirror our own, and consequently, where life could potentially flourish. A special emphasis is placed on more exotic systems. For example, planets orbiting binary stars experience bizarre illumination cycles, while icy worlds with internal tidal heating might conceal liquid oceans beneath massive sheets of ice, suggesting that even in such harsh environments, life could exist, albeit in forms very different from ours. Beyond searching for direct biomarkers, scientists also rely on indirect indicators of life. The existence of stable oceans, tectonic activity, volcanoes, and shifting climates all suggest a dynamic system capable of supporting the complex chemical cycles required for biology. When you combine this information with atmospheric observations, you can build a comprehensive model of a planet's potential to host life. This pursuit also forces us to consider forms of existence that are radically different from those on Earth, such as extremophiles that can withstand intense heat, radiation, low pressure, or frozen environments, thereby broadening the criteria for habitable worlds. Every single new discovery, whether it's a confirmed biomolecule or a detailed atmospheric spectrum, moves us closer to a profound realization. The universe is likely teeming with countless worlds, each offering a unique set of conditions for life. As you absorb these stories, you begin to perceive the underlying harmony and boundless diversity of the cosmos. It awakens you to the possibility that somewhere out there, on planets far from our own, entirely different realities exist where life thrives in the most unexpected forms, maintaining the slow, steady rhythm of the universe. The very discovery of exoplanets would be unattainable without highly precise methods of observation and analysis. After all, you must remember these worlds are at immense distances from us, and their faint light is typically drowned out by the glare of their host stars. To overcome this, modern astronomers utilize several different approaches, each enabling them not only to detect a planet, but also to investigate its atmosphere, determine its mass, chart its orbit, and even learn about its climate. One of the most established and reliable techniques involves measuring a star's radial velocity. As a planet orbits its star, its gravitational pull induces slight oscillations in the star itself, which causes the spectrum of its light to shift due to the Doppler effect. These wobbles are so subtle that they can only be detected with high-precision spectrometers. By analyzing these shifts, astronomers can deduce a planet's mass and orbital characteristics, a method that famously led to the first-ever confirmation of a gas giant orbiting another star. Another technique that has become especially prominent in recent years is the transit method. When a planet crosses in front of its star from our viewpoint, it causes a slight, temporary dip in the star's brightness. Telescopes record these regular dimming events and translate them into light curves, which signal a planet's presence. Analysis of these transits allows you to calculate a planet's diameter, and when paired with radial velocity data, its density. This method is particularly valuable for studying atmospheres, as starlight passing through the planet's gaseous envelope leaves a spectral fingerprint containing potential biomarkers and other chemical traces. Microlensing is a fascinating method grounded in Einstein's gravitational principles. When a massive object like a star passes in front of a more distant one, its gravity bends and magnifies the background star's light. If that foreground star has a planet, it contributes an additional brief magnification that observers can spot, allowing you to find planets far from their suns, including cold worlds and even rogue planets unattached to any star. Equally significant is direct imaging, which is used to actually visualize exoplanets. Using specialized tools like coronagraphs to block the overwhelming stellar light, scientists can capture the faint glow of the planet itself, which in turn enables the study of its cloud systems, atmosphere, and even seasonal variations on its surface. Modern missions, such as Kepler and the Transiting Exoplanet Survey Satellite, or TESS, are dramatically expanding the horizons of exoplanet detection. They are capable of sensing changes in stellar brightness of just a few thousandths of a percent, allowing astronomers to build statistical models about the prevalence of different types of planets. Thanks to these constant observations, scientists are creating vast catalogs of exoplanets, classifying them by size, type, and orbital features, and modeling their potential for habitability. It is vital to recognize that combining these different methods dramatically boosts the accuracy of our knowledge. For instance, transits tell you a planet's size, radial velocity reveals its mass, and spectroscopy deciphers the chemical composition of its atmosphere. A joint analysis of all this data allows scientists to construct a holistic portrait of a world, its structure, its physical properties, and its possible climate. Each of these methods opens incredible opportunities for discovery, leading us to find super-Earths in habitable zones, to get information about winds and precipitation, and even to glimpse a distant planet's color, temperature, and atmospheric dynamics. Ultimately, studying the methods of exoplanet detection is more than just an exercise in technical progress. It is a philosophical dive into the cosmos itself. Each technique serves as a tool for expanding your perception of the universe, allowing you to feel its immense depth and complexity. These methods are our windows to other worlds, offering a glimpse into what might be possible across the vast expanse of space. You come to understand that every planet is a distinct world, each with its own history, atmosphere, and set of conditions. Their discovery transforms the abstract into the tangible, expanding your imagination to grasp the sheer diversity of the cosmic landscape and the mysteries it still conceals. Each method of discovery opens a doorway to new worlds, inviting you to explore the unknown and perceive the harmony within the infinite cosmos, which can create a profound sense of tranquility as you listen, before drifting off to sleep. No exoplanet is an island. Each one is an integral part of a larger system, continuously interacting with its parent star, neighboring planets, and other celestial bodies. By studying orbital dynamics, we learn how these planetary systems are born, what keeps planets in their stable paths, and which cosmic forces shape their climate and long-term stability. Every observation of these orbits is like deciphering an ancient text written in the language of light and gravity, which slowly unveils the universe's inherent grandeur and order. Planetary orbits themselves display incredible variety, ranging from nearly perfect circles to ellipses stretched to astonishing extremes. Worlds in circular orbits tend to experience relatively stable conditions, with only moderate shifts in temperature and light. In contrast, those with elliptical orbits undergo dramatic periodic changes in their distance from the star, which results in significant seasonal temperature swings, altered atmospheric circulation, and fluctuating light intensity, creating cycles that can be far more extreme than Earth's seasons. In systems containing multiple planets, the gravitational interplay between these worlds becomes a critical factor. These interactions can lead to minor orbital deviations, establish resonant patterns, or even foster long-term instability. For instance, when two planets fall into an orbital resonance, their rotational periods become linked by a simple ratio, resulting in beautifully synchronized cycles of movement. Conversely, the powerful gravitational pull of larger planets can force smaller bodies into more distant or precarious orbits, sometimes ejecting them from the system entirely. Scientists give special consideration to the habitable zones within planetary systems, which are the specific regions where temperatures are just right for liquid water to exist on a planet's surface. A planet's stable and prolonged presence within this zone is determined by its distance from the star, the shape of its orbit, and its gravitational relationship with other planets. These very conditions are considered essential for the emergence and continuation of life as we know it. Exoplanets are found not only in systems with a single star, but also in those with multiple suns. Within a binary star system, a planet might orbit one star while being periodically influenced by the gravity of the second, or it could trace a path around both stars at once. These complex arrangements, which astronomers refer to as plural or multi-star systems, produce truly unique conditions for light, temperature, and seasonal cycles, showcasing the wonderfully diverse ways planets can form. The dynamics of a planetary system have a profound impact on the climates of its worlds. For example, tidal forces that arise from close proximity to a massive celestial body can generate internal heat, which in turn can power volcanic activity and the movement of tectonic plates. On frozen exoplanets, this same tidal heating could potentially sustain liquid oceans beneath the ice, creating a possible haven for life on worlds far from their star's warmth. There are also planets that follow exotic orbital paths, such as those with highly elongated trajectories or retrograde orbits, where they travel in the opposite direction of their star's rotation. These unusual worlds provide scientists with a rare opportunity to witness uncommon dynamic processes, which helps them study the stability of orbital systems and model how planetary arrangements evolve over millions of years. Furthermore, the orbits of smaller bodies like comets, asteroids, and dwarf planets play a significant role in a system's formation and ongoing development. These objects can act as cosmic couriers, delivering water and organic compounds to planets, or they can trigger transformative collisions and alter orbital paths. All these interactions contribute to a slow, intricate, and harmonious cosmic rhythm that guides the evolution of entire planetary systems. Investigating these distant exoplanetary systems not only deepens your understanding of conditions on other worlds, but also sharpens your appreciation for the unique stability and harmony of our own solar system. Every celestial movement and every orbit is a step in a vast cosmic dance that has unfolded over billions of years, inspiring a feeling of infinite order and peace. Immersing yourself in this knowledge before sleep allows you to connect with the unhurried pulse of the universe, sensing its magnificence, beauty, and the profound calm that reigns among the stars. The atmosphere of a planet is its invisible yet essential cloak, a layer that sculpts the climate, shields the surface, and ultimately dictates the potential for life. The exoplanets identified over the last few decades reveal just how varied atmospheric conditions can be across the galaxy. Each atmosphere is a unique chemical and physical system, and by studying its composition, you can begin to comprehend the processes at play on that world, from its temperature fluctuations to the chemical reactions that might hint at life. To study exoplanetary atmospheres, scientists employ a technique known as spectroscopy. When a planet transits or passes in front of its star, a fraction of the starlight filters through its atmospheric layer. The gases present absorb light at specific wavelengths, leaving behind a distinct fingerprint of dark lines in the star's spectrum. An analysis of these lines can confirm the presence of compounds like water vapor, methane, carbon dioxide, and ammonia, with the simultaneous detection of oxygen and methane potentially signaling biological processes akin to those on Earth. The makeup of an atmosphere directly governs a planet's climate. Worlds with thick, gaseous envelopes, such as gas giants, are home to powerful winds and colossal storms that can rage for centuries. On terrestrial planets, however, a thinner atmosphere typically fosters more temperate conditions, where you would find the formation of clouds, precipitation, and regular temperature cycles. It is the atmosphere that regulates and distributes heat across the surface, and it also drives the dynamics of any oceans that might exist. Cloud systems on exoplanets also perform a vital function in shaping their environments. On certain gas giants, these clouds might be composed of ammonia, sulfur, or even exotic forms of ice crystals. These formations are responsible for reflecting starlight, which gives the planet its distinct color. And they are also the engines that drive complex weather patterns across the globe, creating a dynamic and ever-changing planetary face. On planets similar to our own, clouds of water vapor can drive cycles of precipitation, generate storms, and establish wind patterns, all of which contribute to a dynamic and often unpredictable climate. By examining these atmospheres, scientists are able to construct models of complex weather phenomena. Powerful winds can effectively transport heat from a planet's equatorial regions toward its poles, while its rotation and the tilt of its axis are responsible for creating distinct seasonal cycles. For worlds with highly elongated orbits, the temperature swings can be immense, leading to profoundly extreme climatic shifts over the course of a single year. These intricate processes serve as a powerful illustration of how the fundamental laws of physics and chemistry combine to forge the unique conditions found on every planet. A significant amount of focus is placed on the concept of habitable zones and the atmosphere's role in determining a world's potential to harbor life. An atmosphere is critical for maintaining liquid water on a planet's surface, trapping necessary heat and shielding it from harmful cosmic radiation, thereby establishing stable conditions for biological processes to emerge. While planets with thin atmospheres or severe climate fluctuations might seem less hospitable, even these harsh environments do not entirely preclude the existence of exceptionally resilient life forms. Advanced observatories like the James Webb Space Telescope give us the ability to analyze the detailed spectra of exoplanetary atmospheres. These powerful tools allow for the investigation of temperature gradients, cloud formations, chemical makeup, and the overall dynamics of an atmosphere. Such data opens a window into the climatic systems of far-off worlds and helps scientists forecast both seasonal and long-term changes on these planets. The climatic events on exoplanets can sometimes be astonishing in their sheer magnitude. On massive gas giants, for instance, storms can develop that span over 1,000 kilometers in diameter. On frozen worlds, powerful winds might transport ice crystals across immense distances. And on planets subjected to intense solar activity, atmospheres can literally boil away, leaving behind colossal tails of gas visible from Earth. These phenomena serve as a poignant reminder that every planet is a vibrant, active world, even when separated from us by millions of light-years. Investigating the atmospheres of these distant planets enables us to gain a more profound insight into the dynamics that govern our own world. We can begin to appreciate how a climate is sculpted by the interplay of solar energy, atmospheric composition, and orbital mechanics, and just how delicate our own Earth is on a cosmic scale. As you reflect on these ideas before sleep, you can immerse yourself in the unhurried rhythm of a planetary atmosphere. You might envision the clouds, winds, and rains of these remote worlds, feeling the deep harmony of the cosmos and the immense tranquility that permeates the space between stars and planets. Every exoplanet represents a complete world, defined by a distinct internal structure that ultimately determines its surface, its climate, and even its atmospheric behavior. The innermost layers of a planet, including its core, mantle, and crust, provide the very foundation for its magnetic field, tectonic activity, and volcanic processes. Delving into these mechanisms allows us to grasp how planets evolve, understand the forces at work deep within them, and see how they interact with the cosmic environment that surrounds them. A planet's core can be thought of as its very heart. Within gas giants, this core might be a dense amalgam of ice, metals, and rock, enveloped by a thick layer of hydrogen and helium. On terrestrial planets like Earth, the core is typically metallic, composed primarily of iron and nickel. This metallic core generates a magnetic field, a crucial shield that protects the planet from solar winds and cosmic radiation, thereby preserving its atmosphere and maintaining conditions suitable for potential life on the surface. Situated above the core, the mantle is composed of viscous, partially molten rock that churns in slow-moving convective currents. This convection is the engine that drives tectonic plate movement, giving rise to mountain ranges, volcanoes, and deep oceanic trenches. On certain exoplanets, the mantle could be so dynamic that the world's surface is in a constant state of flux, forging landscapes that might resemble Earth's, but on a much more dramatic and extreme scale. A planet's crust is its solid external shell, the canvas upon which continents, oceans, and other landscapes are formed. The composition and thickness of this crust are determined by the planet's mass, its internal temperature, and its chemical ingredients. On more massive terrestrial worlds, the crust might be quite thin, whereas on smaller planets it could be thicker and more geologically stable, profoundly influencing the presence of volcanoes and tectonic faults. Geological activity stands as a pivotal expression of a planet's internal structure, with volcanism playing an especially significant role. Volcanic eruptions on exoplanets can build new mountain chains, release vast quantities of gases that alter the climate, and even carry water and organic materials to the surface. These actions remind us that a planet is not a static object, but a living world where internal energy is continuously converted into motion, heat, and chemical change. The internal architecture of a planet also shapes its orbital and climatic behavior. Worlds with active mantles and cores can experience tidal heating, especially if they orbit close to a massive star or another large planet. This internal heating can sustain geological activity, generate subsurface oceans on icy worlds, and influence the atmosphere, helping to create stable climatic conditions, even in the far reaches of a solar system. By comparing the internal structures of exoplanets with that of Earth, we gain a clearer appreciation for our own planet's distinctive qualities. Earth is characterized by a thin crust, a dynamic mantle, and a liquid metallic core, a combination that generates a stable magnetic field and supports life. On other worlds, these conditions can be vastly different. Some may have stagnant mantles, cold cores, or surfaces that are completely frozen over, making them uninhabitable, yet captivating subjects for scientific study. Exploring the inner workings of exoplanets broadens our comprehension of the physical laws that govern planetary formation, and reveals how these processes give rise to the unique environment of each individual world. As you drift into sleep, you can imagine the depths of these planets, their molten cores, their shifting mantles, and their forming crusts, and sense the profound calm and harmony of the cosmos, knowing that each planet moves to its own slow, majestic rhythm. The diversity of exoplanets extends far beyond just their orbits and atmospheres to encompass their fundamental physical traits. To make sense of this variety, scientists categorize them based on size, mass, composition, and temperature, which provides critical insights into how planetary systems evolve and which worlds might harbor life. As you listen to this exploration before drifting off to sleep, you can connect with the unhurried rhythm of the cosmos, feeling its immense scale and harmony. The first category we encounter is the gas giants, worlds that are tens or even hundreds of times more massive and voluminous than our own Earth. Composed mainly of hydrogen and helium, they may conceal a solid or icy core deep within. These colossal planets can be found orbiting either very near to or quite far from their parent stars, leading to dramatically different conditions. Gas giants situated close to their stars are known as hot Jupiters, characterized by incredibly high temperatures, ferocious winds, and gigantic multi-year storms. In contrast, their more distant counterparts are like colder versions of Jupiter and Saturn, featuring distinct atmospheric bands and layers of clouds. A second major category consists of Neptune-like planets, or mini-Neptunes, which are smaller than gas giants, but still possess a substantial gaseous envelope, often containing hydrogen, helium, and methane, giving them a distinct blue tint visible across vast distances. Our third classification covers terrestrial, or rocky planets. These worlds possess solid surfaces and have the potential for oceans, atmospheres, and even volcanic processes. Exoplanets resembling Earth within the habitable zone are a primary focus in the search for extraterrestrial life, as their mass and radius are comparable to our own, and their atmospheres could potentially sustain liquid water. The variety among them is staggering. Some might be arid desert worlds. Others could be covered entirely by oceans, while still others remain hidden beneath thick, impenetrable cloud layers. Beyond these more common types, there are truly exotic planets with highly unusual characteristics. For instance, ultra-hot Jupiters reach such extreme temperatures that metals and silicate particles can exist as a gas on their surfaces. Some planets have retrograde orbits, moving in the opposite direction of their star's rotation, while others possess ring systems far more massive than Saturn's, or follow highly eccentric paths that cause their distance from the star to vary by dozens of times. Planetary mass provides another crucial layer of classification. Super-Earths are worlds several times more massive than our planet, but smaller than the gas giants, and their intense gravity would profoundly influence their atmosphere, surface, and any potential life. Conversely, planets with less mass than our own are termed sub-Earths, where conditions can be more severe due to weaker gravity and thinner, more fragile atmospheres. The chemical makeup of these planets is also incredibly varied. Gas giants are overwhelmingly composed of hydrogen and helium, whereas icy planets are rich in water, ammonia, and methane. Terrestrial worlds like our own are formed from silicon, iron, magnesium, and oxygen. These elements are the building blocks of minerals, rocks, and planetary cores, which in turn drive geological activity, shape magnetic fields, and define the climate. This system of classifying exoplanets allows scientists to organize their observations and predict the features of newly found worlds. Each planetary type represents a unique realm with its own physical laws and climatic conditions, all fitting within the grand harmonious structure of planetary systems. As you contemplate these worlds before sleep, imagining their sizes, colors, and compositions, you can truly appreciate the universe's magnificent diversity. The journey to comprehending these distant worlds starts with understanding how we even find them in the first place. Despite their immense distances, often tens or hundreds of light years away, modern astronomy has devised remarkably clever methods for their detection. As you settle in for the night, let your mind drift into this world of scientific discovery, sensing the inherent harmony of the cosmos. One of the most widely used techniques is the transit method, which relies on a planet periodically passing in front of its star, creating a miniature eclipse. This event causes a slight, temporary dip in the star's brightness that our telescopes can record. By carefully analyzing the depth and frequency of these transits, astronomers can deduce the planet's size and the duration of its orbit. Furthermore, when the star's light filters through the planet's atmosphere during a transit, we can study its chemical makeup, detect clouds, and even observe weather patterns. Another key technique is the radial velocity method, also known as the Doppler method. A planet and its star both orbit a shared center of mass, which causes the star to exhibit a subtle wobble. These movements induce tiny shifts in the star's spectral lines, which can be measured with extraordinary precision, revealing the planet's mass and orbital details. This method is particularly adept at finding massive planets that orbit close to their stars. Direct imaging methods also exist, though they are employed less frequently due to their technical difficulty. Planets are vastly fainter than their brilliant stars, but by using advanced techniques to block the star's glare, modern infrared telescopes can sometimes capture actual images of these worlds. These observations are invaluable for studying the atmospheres, cloud structures, and reflected light from gas giants and planets with thick atmospheric layers. An equally compelling technique is gravitational microlensing, which leverages the principles of gravitational lensing. When a massive object, such as a star accompanied by a planet, moves in front of a more distant star, its gravity bends and amplifies the background star's light for a brief period. Monitoring these fleeting changes in brightness enables the detection of planets that are extremely far away and otherwise invisible. Space-based observatories like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, have completely transformed exoplanet research, with Kepler alone using the transit method to monitor hundreds of thousands of stars for the telltale signs of orbiting worlds. Missions like TESS extend our search to nearby stars, revealing planets that are brighter and more accessible for in-depth investigation. This effort yields an unprecedented volume of data, which allows for the compilation of detailed exoplanet catalogs that document crucial information like planetary sizes, masses, and orbital paths. By integrating various techniques such as transit photometry, radial velocity measurements, direct imaging, and gravitational microlensing, you can build a truly holistic view of these distant planetary systems. Each of these detection methods offers a unique piece of the puzzle, and they work in concert to provide a complete picture. For example, one technique reveals a planet's size, another its mass, a third can analyze its atmospheric properties, and a fourth might even allow you to see the planet directly against the brilliance of its star. With this combined information, astronomers are able to construct sophisticated models of exoplanets and their orbital dynamics, enabling them to predict climates and better understand the processes occurring deep within these worlds. Studying these detection methods reminds you just how fine the line is between observation and true understanding, as every discovery demands careful analysis, extraordinary patience, and immense precision. As you reflect on this, you can imagine telescopes capturing the faintest signals of light, the subtle wobbles of stars, and the dim glow of faraway planets, feeling a connection to the magnificent harmony of the universe. An exoplanet's atmosphere is its invisible wrapping, but it is this envelope that ultimately dictates the climate, weather, and conditions for any potential life. Some of the most profound discoveries in modern astronomy are directly tied to the study of these atmospheres, which can tell you about the temperature, composition, clouds, and even the dynamic forces at work on these distant worlds. As you contemplate this, you might picture these unseen layers of gas slowly blanketing alien planets, sensing a connection to the deep and resonant harmony of the cosmos. The principal instrument for this exploration is spectroscopy, a method that provides a window into the chemical makeup of these worlds. When light from a star filters through a planet's atmosphere during a transit, specific wavelengths are absorbed by the gases present. By meticulously analyzing these resulting spectral lines, astronomers can identify which elements and molecules make up that atmosphere. It is through this very process that we have detected water vapor, methane, carbon dioxide, and even sodium and potassium on some gas giants. This data is essential for creating a chemical map of the atmosphere and for deciphering the climactic processes that shape the planet. The cloud systems on exoplanets can be incredibly diverse, with their composition depending on the planet's temperature and atmospheric gases. You might find clouds formed from water, ammonia, and methane, or even from more exotic substances like molten metal and silicate particles. On hot Jupiters, these cloud systems generate distinct banded layers and colossal storms that churn around the planet at breathtaking speeds. Remote observations enable us to capture these structures, which are then used to create visual models that illustrate these dynamic atmospheric behaviors. Atmospheric temperature is governed by several factors, including the planet's distance from its star, its total mass, its atmospheric composition, and its unique orbital characteristics. On worlds orbiting very close to their stars, temperatures can soar to 1,000 degrees Celsius. In contrast, on distant, frozen planets, they can plummet to hundreds of degrees below zero. These extreme temperature differences are the engines that drive powerful winds, convective currents, and chemical reactions, giving rise to truly unique weather systems. The movement of gases within an atmosphere also profoundly influences its climate and potential weather patterns. For instance, on planets with very fast rotations, you will find powerful wind currents forming along the equator. On worlds that rotate more slowly, vertical convection might be the dominant force, creating enormous columns of clouds. Understanding these processes is crucial for evaluating a planet's habitability and for predicting how its climate might evolve over its long history. Occasionally, astronomers witness a phenomenon known as atmospheric escape, where a planet loses its gases to space because of intense radiation from its star. This has been observed on hot Jupiters, where hydrogen and helium are gradually stripped away, forming vast comet-like tails that trail behind the planet. Such processes demonstrate that an atmosphere is a dynamic system, one that is in a constant state of interaction with its surrounding cosmic environment. Investigating exoplanetary atmospheres represents a critical step in the search for potential life beyond our solar system. By identifying the composition of gases, confirming the presence of water, observing clouds, and finding climate-stabilizing elements like carbon dioxide and nitrogen, you can begin to speculate which planets might be hospitable to life. Every spectral signal, and each measured absorption line, serves as a small clue to a world you cannot see directly, but which reveals itself to a careful and attentive observer. As you think about this, you can picture the invisible clouds, winds, and chemical reactions unfolding on these faraway planets. An atmosphere is truly the breath of a world. It is the signature of its life and its interaction with the cosmos. By delving into these atmospheric layers, you can begin to appreciate the immense depth and complexity of the universe, where every world moves to its own slow yet majestic rhythm. The climate on any given exoplanet is a living, dynamic process that forges a unique environment on each world, shaped by a multitude of factors. These include its distance from the parent star, the makeup of its atmosphere, its specific orbital configuration, and even the planet's own internal energy. You can almost envision the limitless expanses of clouds, oceans, ice, and winds, all slowly rotating around these distant suns. On hot Jupiters, which are planets situated extremely close to their stars, the stark temperature differences between the day and night sides generate colossal atmospheric currents. Winds on these worlds can reach speeds of thousands of kilometers per hour, driving clouds across the surface and forming impressive banded structures. These planets are racked by constant, immense storms that can persist for decades, creating dynamic atmospheric patterns that unfold like living canvases for observers using powerful telescopes. In stark contrast, cold and icy planets offer a completely different climactic picture. On these worlds, temperatures can fall to hundreds of degrees below zero, resulting in the formation of vast ice sheets and entirely frozen oceans. Any atmosphere that exists is typically extremely thin, characterized by slow but persistent winds. At times, these planets feature atmospheric hazes composed of frozen gases, which gradually settle onto the surface and create intricate patterns reminiscent of snow and ice on Earth, but on a truly planetary scale. Exoplanets, situated within the habitable zones of their stars, where temperatures are more moderate, often feature climatic conditions reminiscent of Earth's. In such environments, you can find oceans, cloud formations, and atmospheric systems that regulate temperature, driving cycles of rainfall and wind. These planetary processes hinge on the specific makeup of the atmosphere, particularly the presence of heat-trapping gases like water vapor and carbon dioxide, which can foster a complex and stable climate where liquid water persists. Yet the universe is also home to far more exotic climate scenarios. On worlds with unusual or highly eccentric orbits, you would witness dramatic temperature shifts throughout a single planetary year, leading to seasons of extreme heat and cold. Imagine planets where the clouds are not water, but are instead composed of molten metals or silicates, or others where they consist of ammonia and methane. Such variations give rise to an incredible diversity of weather systems that stretch beyond anything we might normally conceive. Oceans and other bodies of water on exoplanets can exist in either a liquid or frozen state. On frigid worlds, vast liquid oceans might be concealed beneath immense sheets of ice, kept from freezing by the planet's own internal heat and the immense pressure from above. Conversely, on hotter planets, oceans might undergo constant, vigorous evaporation, creating the dense clouds and rain cycles that distribute heat and establish intricate climatic zones across the surface. Storms, hurricanes, and vortices on these distant worlds can be truly staggering. From immense atmospheric maelstroms churning on gas giants, to more localized tempests on rocky planets. You could find worlds where massive and frequent lightning bolts flash through clouds of molten metal or ammonia. On others, powerful winds might sweep along clouds of frozen gases, generating an effect of perpetual atmospheric motion, as if the planet itself were breathing. Investigating these climatic processes enables astronomers to better evaluate the potential habitability of an exoplanet and to forecast the conditions that might allow life to emerge. Each world is a unique case, its climate a delicate and intricate balance of physical, chemical, and astronomical influences. Pondering this allows you to travel in your mind above alien clouds, oceans, and icy plains, watching as every component of the atmosphere and climate interacts in a seamless and magnificent cosmic performance. The interior of a planet remains hidden from direct observation. Yet, it is this internal world that dictates the nature of its surface, climate, and atmosphere. The geological processes of exoplanets are the unseen engine driving them from within, responsible for creating mountains, volcanoes, and continental rifts. This internal activity can even generate the magnetic fields that shield a planet's atmosphere from the harshness of cosmic radiation, offering a glimpse into the slow, powerful movements of rock and magma that can sustain a world's harmony. One of the primary drivers of this activity is the planet's internal heat, which is a combination of residual energy from its formation and ongoing heat from the radioactive decay of elements in its core. This thermal energy fuels convection within the mantle and melts rock, which in turn powers volcanoes and tectonic activity. On gas giants, this internal heat source creates powerful atmospheric currents and complex cloud structures, while on Earth-like worlds, it manifests as the movement of lithospheric plates and volcanic eruptions. Volcanoes on exoplanets can vary from modest formations to colossal structures that launch lava and gases hundreds of kilometers into the sky. This volcanic activity does more than just sculpt the surface. It also injects gases into the atmosphere that help regulate the climate. On some alien worlds, volcanoes might expel methane, ammonia, or even molten metals, resulting in exotic lava flows and strange metallic clouds. These processes can unfold over millions of years, methodically reshaping the landscape and transforming the planet's climate. Tectonic processes also have a fundamental role in shaping a planet. The shifting of lithospheric plates gives rise to mountain ranges, deep oceanic trenches, and vast fault lines. On worlds with active tectonics, the surface is in a constant state of renewal, a process that aids in carbon recycling and the maintenance of a stable climate. In contrast, planets without tectonic activity may have ancient surfaces, heavily scarred by craters and covered in ice, with few mechanisms for redistributing heat and chemicals. Magnetic fields represent another critical element of a planet's internal dynamics. They are generated by the motion of a liquid metallic core and form a protective shield against solar and cosmic radiation. Planets that possess strong magnetic fields are capable of holding on to their atmospheres, preventing them from being stripped away by fierce stellar winds. Without such a magnetic shield, a planet's atmosphere can slowly erode into space, causing its surface to grow colder and far less hospitable to life. Some exoplanets showcase truly extreme geological phenomena. For instance, planets orbiting very close to their stars may experience intense tidal stretching, a process that heats their inner layers and triggers widespread volcanic activity. You might see something similar on the moons of gas giants, akin to Jupiter's moon Io in our own solar system, where volcanoes continuously eject sulfur and other compounds, creating brightly colored surfaces and unusual atmospheric effects. All of these internal mechanisms, from flowing magma and tectonic shifts to volcanic eruptions and magnetic fields, collectively determine a planet's dynamics, its climate, and its capacity to support life. It's fascinating to imagine that invisible force moving slowly beneath the surface, which is responsible for crafting the landscapes, atmospheres, and potential for life on these distant worlds. A planet never exists in isolation. It is in constant interaction with its star and its planetary neighbors. An orbit is the invisible path a planet follows, guided by the laws of gravity, which establishes the harmony and rhythm of a cosmic ballet. If you picture it, you can see millions of worlds, both large and small, in a slow, graceful revolution around their suns, a delicate stability maintained over billions of years. Each orbit has its own unique character. It can be nearly circular, leading to a consistent cycle of seasons and temperatures, or it can be highly elongated, resulting in extreme fluctuations in the conditions on the planet's surface. For some exoplanets, intense tidal forces from their host star result in synchronous rotation, where one side is locked in permanent daylight and the other in perpetual night. This phenomenon gives rise to extreme and unusual climate zones, creating scorched landscapes on the illuminated hemisphere and vast frozen deserts on the side shrouded in eternal darkness. These tidal interactions extend beyond just rotation. By constantly stretching and compressing a planet, they can generate significant internal heat, fueling the kind of volcanism and tectonics seen on Jupiter's moon Io, and potentially sustaining geological wonders deep beneath the surface of rocky exoplanets. Resonances between planets serve as another beautiful example of gravitational harmony at work. In systems with multiple planets, their orbits can become linked in a resonance, where for every 3 trips one planet makes around its star, a neighbor completes exactly 2. This gravitational lockstep stabilizes the entire system, preventing chaotic orbital decay and establishing a rhythmic, predictable pattern of movement that you could visualize as the slow, deep breathing of the cosmos itself. Within these multi-planet systems, the worlds don't just influence each other gravitationally. They also indirectly alter orbits, inclinations, and rotation periods, giving rise to incredibly complex dynamics. A planet might experience slight wobbles that subtly change its climate and tidal patterns, yet the system as a whole can maintain its stability over billions of years. This remarkable endurance is the product of a delicate balance of forces, visible in every celestial body's journey around its star. Certain exoplanets display truly unique orbital behaviors that create exotic conditions affecting their climate, geology, and atmosphere. On worlds orbiting close to red dwarfs, for instance, the tidal slowing of their rotation can lead to the formation of stable wind patterns and distinct weather zones. In systems with more than one star, planetary orbits can become intricate and elegant, resembling a cosmic dance between multiple suns. Understanding these orbital dynamics is crucial for assessing the potential habitability of exoplanets, as the distribution of energy, degree of internal heating, and nature of climatic cycles all depend on how a world moves through space. As you picture these distant systems, you can imagine the smooth, unhurried motion of a planet in its orbit, a harmony of force and energy that creates a stable cosmic rhythm, potentially sustaining both life and the profound beauty of that faraway world. Exoplanets present an astonishing range of diversity, with each one representing a miniature universe governed by its own unique conditions, climate, atmosphere, and geology. Imagining these worlds, you can embark on a slow journey through the endless expanse of space, where each planet seems to whisper its secrets, and telescopes gently pull back the curtain on their breathtaking realities. One of the most well-known classes of exoplanets is the hot Jupiters, which are gas giants orbiting incredibly close to their stars, sometimes at less than a third of the distance between Earth and the Sun. Their atmospheres are superheated to several thousand degrees, driving furious winds and storms that rage at thousands of kilometers per hour. Across these turbulent worlds, clouds composed of metals and silicates drift through the atmosphere, forming the swirling bands and patterns that scientists are able to observe through spectroscopic analysis. At the opposite extreme, you can find icy super-Earths, which are massive, rocky planets with frigid temperatures dropping hundreds of degrees below zero and surfaces likely covered in thick layers of ice. Despite the cold, internal heat on these worlds could sustain liquid oceans beneath their frozen crusts, creating hidden environments where the conditions for life would be starkly different from Earth's, yet remain fascinating to astrobiologists. These planets frequently possess dense atmospheres, heavy with methane or ammonia, which in turn generate unique cloud formations and other atmospheric phenomena. Super-Earths, which are more massive than our planet but smaller than gas giants, showcase a wide array of potential characteristics. Some of these worlds are dense and rocky, with gravity much stronger than our own, and they may have thick atmospheres rich in carbon dioxide that trap heat through a powerful greenhouse effect. Others could be water worlds, with vast oceans covering nearly their entire surface, leading to gentle weather cycles and extensive cloud systems. You can also find exoplanets with highly unusual orbital paths, such as those on extremely elongated orbits that cause drastic temperature swings throughout their year, heating one side to incredible temperatures while the other plunges into a deep freeze. Astronomers give special consideration to planets situated within the habitable zone, an orbital region around a star where temperatures are just right for liquid water to exist on a planet's surface. It is in this zone that worlds with mild climates, stable oceans, and atmospheres suitable for life's emergence could form. The discovery of such planets fuels the scientific and public imagination, opening a window into the possibility of life beyond our solar system and the potential future of humanity itself. Every exoplanet is a distinct world, sculpted by billions of years of evolution, internal activity, orbital mechanics, and atmospheric dynamics. As you contemplate this cosmic kaleidoscope, you can picture the slow rotation of gas giants, the churning oceans of super-Earths, the sparkle of immense ice sheets, and the shimmering cloud patterns on the horizons of distant worlds. This reminds us of the universe's infinite variety, and how each planet represents a small story that we are only just beginning to read. Our understanding of exoplanets starts with their discovery, and despite the trillions of kilometers separating us, scientists have developed methods to perceive these remote worlds through subtle shifts in starlight and motion. You can imagine these invisible rays of light journeying through space, carrying the secrets of exoplanets like a gentle whisper from across the galaxy. Among the most effective of these detection techniques is the transit method. When a planet crosses in front of its parent star, it casts a shadow that causes a brief dimming of the star's light. This reduction in brightness is minuscule, often just a few hundredths of a %, yet our modern telescopes are sensitive enough to register it. By meticulously analyzing these subtle fluctuations, we can deduce a planet's size and orbital period, and sometimes even glimpse the makeup of its atmosphere as starlight filters through its gases and clouds. Another powerful technique involves measuring the radial velocity of a star. A planet's gravitational pull causes its star to wobble slightly as it orbits. This movement creates a detectable shift in the star's spectral lines, either toward the red or blue end of the spectrum, which can be measured with extraordinary precision. These minor oscillations allow us to calculate the planet's mass and orbital details, revealing a celestial dance that, while invisible to the naked eye, is perfectly clear through our instruments. Gravitational lensing offers a rare, yet spectacular method for discovery. If a massive object, like a planet, happens to pass in front of a distant star, its gravity will bend the light from the background object, acting as a lens. This effect can magnify or alter the distant star's brightness, enabling us to find planets that would otherwise remain hidden, and to even approximate their mass and distance from their own star. Thanks to incredible technological advancements, we are now able to directly observe exoplanets. This challenging feat requires us to block out the overwhelming glare of the host star to capture the planet's faint, reflected glow. Using sophisticated instruments like coronagraphs and interferometers, astronomers can produce images where you can distinguish features such as atmospheric clouds, ice caps, or perhaps even variations in surface color, appearing like cosmic watercolors painted by the universe for a patient viewer. By integrating these various methods, we can do more than just find exoplanets. We can begin to characterize them in detail, studying their atmospheres, temperatures, and chemical compositions. Each technique adds a crucial piece to the puzzle. One determines size, another reveals mass, a third analyzes the atmosphere, and a fourth lets us see the planet itself. This synergy allows astronomers to construct intricate models of alien worlds and their solar systems, helping to predict their climates and understand their inner workings. Often, these methods intersect to build a more robust understanding. For instance, a transit detection can be confirmed with radial velocity measurements, while direct observations can refine our knowledge of atmospheric properties. This collaborative approach builds a comprehensive portrait of a distant world that once existed only in theory. Every new discovery is a small miracle, revealing that planets around other stars are just as varied as those in our own cosmic neighborhood, and frequently far more exotic. Imagine yourself as a traveler, gliding silently between the stars, observing their hidden companions. You are slowly unveiling new horizons, where each world has its own unique story to tell. An exoplanet's atmosphere is its invisible wrapping, a fluid, gentle envelope that nonetheless exerts a profound influence on its climate and potential for life. As you can imagine, the atmospheres on these distant worlds are astonishingly diverse, with clouds, winds, and layers of gas swaying in delicate, harmonious motion billions of kilometers from Earth. The specific composition of an atmosphere is shaped by the planet's mass, its temperature, and the history of its formation. On gas giants, like hot Jupiters, hydrogen and helium are the main components, but their upper layers can host clouds made of metals, silicates, or even iron. These unusual cloud formations produce stunning color palettes, bands of golden orange, deep purple vortices, and silvery polar caps, all shifting like slow-motion watercolors across the cosmos. On rocky super-Earths, you might find atmospheres containing carbon dioxide, methane, ammonia, or water vapor. The thickness and density of this gaseous layer determine the surface temperature, drive a greenhouse effect, and govern complex wind patterns. On some of these worlds, astronomers have detected immense storms that, much like on Earth, travel along meridians and redistribute heat from the sunlit side of the planet to its dark side. Of particular fascination are the habitable zones around stars, where exoplanets might possess atmospheres rich in oxygen and nitrogen, much like our own, which would support stable climate cycles. With relatively mild temperatures between day and night, these worlds could sustain liquid water and predictable weather. You can almost feel the slow, steady breathing of such a planet, the rhythm of winds, rains, and clouds moving over oceans and continents in a gentle, harmonious dance. In certain cases, an exoplanet's atmosphere can be extraordinarily dynamic. For example, on worlds orbiting very close to their stars, intense tidal heating can generate constant, ferocious winds that reach speeds of thousands of kilometers per hour. Here, clouds are ripped into long ribbons as chemical elements engage in complex, energetic reactions. These processes create vivid scenarios that, while not directly visible, can be reconstructed by scientists using spectroscopy and advanced modeling. It is also fascinating to consider how atmospheres can transform over time. The constant influence of the parent star, gravitational interactions with other planets, and internal geological heat all contribute to the slow evolution of a planet's gaseous layer. Some worlds may gradually lose their atmospheres to space, while others build them up through volcanic eruptions and chemical processes. This quiet, majestic dance has been unfolding for billions of years, sculpting unique worlds with distinct conditions on every planet. Each atmosphere is ultimately a window into the soul of a distant world, a living and constantly changing system that creates weather patterns unlike anything we know. As you contemplate the cosmos, you can picture the clouds drifting slowly over these alien landscapes, the winds carrying warmth across their surfaces, and the shifting colors of their skies. This vision of calm, harmonious movement can lull the mind while opening your imagination to the limitless horizons of the universe. As you listen before resting, you can picture the invisible energy stirring a planet's atmosphere, giving rise to both gentle and sudden fluctuations. Imagine clouds sweeping across a distant horizon as cosmic winds whisper their silent tales over billions of kilometers of empty space. On gas giants orbiting close to their stars, you'll find climate cycles of extraordinary ferocity, where the most powerful winds propel clouds around the planet at thousands of kilometers per hour. These gales form colossal, banded storm systems that can last for centuries, resembling slowly rotating watercolors against the world's edge, redistributing heat to create a profound harmony from the surrounding chaos. Now, turn your thoughts to rocky super-Earths with thick atmospheres, where wind patterns establish more temperate climatic rhythms. The daily variations in temperature drive the movement of clouds, the formation of rain systems, and the emergence of localized hurricanes. These worlds sometimes face prolonged downpours that saturate their oceans or carve out rivers, while at other times, immense storms block out the sun, painting the sky in shades of gray, blue, and violet. Exoplanets in elongated orbits are especially compelling, as their climates undergo dramatic shifts over the course of their year. As one of these planets swings near its star, the surface heats up, unleashing powerful winds and causing oceans to evaporate. Then, as it moves away, the atmosphere cools, allowing ice sheets to form and air currents to slow. This rhythm establishes seasonal cycles completely alien to our own, generating unique weather phenomena that are easy to visualize as you listen. On habitable worlds, however, climate cycles can be both mild and balanced. Gentle winds guide clouds over continents and oceans, ensuring stable precipitation and moderate temperatures, creating a sense of peace and order. This entire system acts as the planet's soft respiration, a captivating and soothing rhythm akin to a silent cosmic melody. All this variety gives rise to a complete symphony of weather, where vortexes, clouds, storms, and rains interact to transfer energy and maintain atmospheric dynamics. Contemplating these worlds before sleep, you can sense the harmony in this movement, where every storm and every raindrop contributes to the grand cosmic canvas that the universe has been creating for billions of years. These phenomena remind us that every world is alive and beautiful in its own way, teaching us to see change as a natural part of existence. Even the fiercest storms are merely transfers of energy that ultimately forge balance and harmony. And as you listen, you can let your mind drift into slumber, filled with visions of distant worlds and the universe's gentle breath. Think of planetary orbits as invisible roads along which worlds journey around their stars, forming majestic and harmonious systems whose trajectories show incredible diversity. You can imagine how billions of kilometers of space are filled with these smooth, slowly turning orbits, where each planet holds its own rhythm and place, composing the music of the cosmos. Many exoplanets reside in multi-planet systems, where their orbits can be in resonance, meaning their orbital periods align in simple numerical ratios, creating a stable cadence. You can picture these planets performing a slow, cosmic ballet, with each step and turn perfectly coordinated with its partners. In other systems, orbits are extraordinarily elliptical, causing a planet to briefly approach its star before retreating for long durations. This movement creates sharp fluctuations in light and temperature, profoundly impacting the atmosphere and the potential for liquid water to exist. There are also gravitational interactions with other massive bodies, such as companion planets or stars in binary systems. These encounters can subtly alter orbits, generate powerful tidal forces, and trigger complex changes in a planet's geology and atmosphere. While such influences can sometimes be catastrophic, they often result in a slow, harmonious redistribution of energy, producing amazing dynamics. These multi-planet systems are incredibly beautiful, sometimes aligning in perfect planes, and other times forming more chaotic, inclined configurations. Regardless of their layout, their movement is like an endless dance where each planet knows its role, and every orbital cycle contributes its own rhythm. Imagining this as you fall asleep, you can feel the quiet, orderly motion soothing your mind like a slow cosmic melody. Scientists also discover rogue exoplanets, wandering through space after being ejected from their home systems. They travel through the void, illuminated only by the distant stars they pass, like wanderers carrying memories of their origins. These free planets are a reminder that the universe is a place where order and chaos coexist to create an amazing diversity of worlds. As you settle in for the night, you can visualize the silent turning of planetary orbits in the cosmic darkness. Picture how these worlds and their stars engage in a perpetual, graceful interaction, composing an unending rhythm of movement that calms the spirit and readies your mind for a profound and gentle sleep. The foundation for this peaceful vision is the habitable zone, a specific region surrounding a star where the conditions are just right for liquid water to potentially exist on a planet's surface. After all, when we contemplate the possibility of life, our thoughts turn to water, the very cornerstone of every living organism on our own world. Imagine the soft radiance of a faraway star gracing the surface of an exoplanet, its light shimmering across oceans, lakes, and rivers, casting a tranquil and quiet glow. A planet's ability to hold on to this precious water is governed by its size and mass, which determine its power to maintain an atmosphere. A world that is too small risks having its atmosphere and water stripped away into space, while a planet that is excessively large could develop a crushing, dense atmosphere, trapping heat and searing its surface with an intense greenhouse effect. Yet within the ideal orbital path known as the Goldilocks zone, conditions are perfectly balanced. Here, water can remain in its liquid state for countless millennia, fostering an environment where complex chemical compounds could form, giving rise to a unique biochemistry, and, just possibly, to life itself. The climate on such an exoplanet might be remarkably temperate and harmonious, with the cycle of day and night establishing a steady thermal rhythm, while winds circulate warmth and clouds deliver life-sustaining rain to the soil and waterways. You can almost feel a soft breeze guiding the clouds across the sky. See the gentle swell of the oceans, and hear the patter of raindrops meeting the ground, all of which evokes a deep sense of peace and serenity. However, even these ideally placed exoplanets can be subject to extreme forces. A particularly volatile star might unleash powerful flares and radiation that can erode an atmosphere, initiate disruptive chemical reactions, and evaporate surface water. Similarly, the gravitational pull from a nearby gas giant could generate massive tides that reshape the distribution of oceans and rivers over time. While these phenomena might appear destructive, they can contribute to a dynamic equilibrium, a state where the planet continuously adapts while still preserving conditions that could support life. Even more captivating are systems that host multiple planets within the habitable zone. Imagine several worlds orbiting at the perfect distance for liquid water, perhaps influencing one another through tidal forces that create slow, rhythmic cycles of ebb and flow, gently shaping their climate, weather patterns, and the very layout of their waters. Envision this process as the gentle respiration of planets, where every droplet of water, every current, and every gust of wind contributes to a grander cosmic harmony. To peer into these distant atmospheres, scientists employ a technique called spectroscopy, meticulously searching for the telltale signatures of water, methane, oxygen, and other gases that might signal biological activity. Each spectrum and every signal serves as a portal into the mystery of another world, inviting you to dream of its placid oceans, winding rivers, and the quiet circulation of air that could sustain it. The habitable zone represents far more than a simple temperature range. It is a realm of immense possibility. In any place where water can flow freely, where an atmosphere provides climatic stability, and where a planet exists in balance with its star and its neighbors, the potential for life in some wondrous form is born. Contemplating these worlds, with their serene oceans, soft starlight, and gentle winds, can create a profound sense of tranquility, guiding your mind toward a state of peaceful, deep rest. The search for exoplanets is an exercise in immense patience and precision, where the faintest signal can announce the discovery of a new world concealed among billions of stars. As you listen, picture enormous telescopes aimed at the infinite blackness of space, gathering ancient light that has journeyed across millions of years to finally reach our instruments. One of the primary tools for this search is the transit method, which detects the minuscule dimming of a star's light as a planet crosses its face. This subtle flicker allows scientists to calculate the planet's size and the duration of its year. Another powerful tool is the radial velocity method, sometimes called the Doppler method, which identifies planets by the slight gravitational influence they exert on their parent stars. This gentle tug causes the star to wobble, a motion that is detectable as a shift in its light spectrum, providing scientists with data to determine the planet's mass and orbital path. You can visualize these unseen gravitational forces orchestrating a silent, precise cosmic ballet, a rhythm our instruments allow us to perceive, turning the universe into a slow and majestic dance. Direct imaging presents a more formidable challenge, but offers an incredibly rewarding glimpse of these worlds. This technique involves carefully blocking the overwhelming glare of a star with instruments like coronagraphs, allowing the faint, reflected light of the planet itself to become visible. Imagine that moment of discovery, seeing a tiny speck of light flicker into view beside its star, like a distant lantern in a dark room, beckoning us to explore its secrets. A further ingenious technique is known as gravitational microlensing. When a celestial body with significant mass passes in front of a more distant star, its gravity bends the light, causing a temporary surge in the star's brightness. If that passing object has a planet in orbit, it adds a unique secondary signature to the event. This method opens a window to discovering even rogue planets that drift untethered through space by letting you picture how vast streams of light are gently warped, unveiling worlds that would otherwise remain entirely invisible. The meticulous care and patience of astronomers enable us not just to find exoplanets, but to explore their climates, atmospheres, and the potential for water and life. As you listen, you can picture how every scientific tool and technique becomes a soft beam of light, gliding over the surfaces of these remote worlds, uncovering their secrets slowly and gently, much like a fable told in the stillness of the night. The discovery of exoplanets serves as a profound reminder that our universe is teeming with unseen worlds, each one singular and filled with mystery. We are only just beginning to grasp the sheer variety of their orbits, dimensions, atmospheres, and the possible forms of life they might harbor. Envisioning these cosmic processes before you drift off can help you connect with the harmony and boundless depth of space, allowing you to sink into a serene and restorative sleep. A planet's atmosphere acts as its invisible cloak, a delicate layer that envelops the surface, shielding it from cosmic forces while shaping its climate and fostering conditions for life. While listening, imagine a faint breeze stirring the clouds as thin veils of gas scatter starlight, casting a gentle twilight and a sense of deep tranquility across that distant world. The variety among exoplanetary atmospheres is astounding. Certain planets, particularly gas giants akin to Jupiter, possess thick, gaseous envelopes composed primarily of hydrogen and helium, occasionally with hints of methane and ammonia. These gases coalesce into dense, smooth clouds that drift slowly over the planet, forming magnificent vortices and gentle bands that resemble the calm currents of a celestial ocean. Visualizing this before sleep, you can almost feel the immense swirls turning gently, like soft music calming your thoughts. On smaller planets with solid cores, the atmosphere might be thinner, yet is no less captivating. There you could discover clouds made of water, carbon dioxide, or even sulfates, which weave intricate patterns and create soft plays of light on the surface. Winds interacting with these clouds work to circulate heat, establishing cycles of rain and atmospheric flows that slowly and placidly animate the planet with its own unique climate. Scientists investigate the atmospheres of exoplanets by using spectroscopy, which involves analyzing the light that filters through the gaseous envelope. Since different chemical elements absorb light at specific wavelengths, they leave behind unique spectral signatures. These signatures allow us to map the atmospheric composition, confirm the presence of clouds, and even detect traces of complex molecules like water or methane, compounds that could be tied to biological processes. Imagine that minuscule particles of light, after journeying for millions of kilometers, arrive carrying information about the quiet, unseen life of a distant atmosphere, which we then patiently decode. Some exoplanets feature a layered atmospheric structure, with dense, warm lower layers and thin, cold upper layers. Within these strata, complex wind patterns emerge, creating gentle vortices that move clouds, distribute heat, and drive unique weather cycles. For planets orbiting very close to their stars, the atmosphere can become incredibly hot, whipped by powerful winds that carry clouds and radiant flashes, like a perpetual, silent storm, slowly carving its path through space. Exploring these atmospheres helps us comprehend climatic systems, search for signs of water and biochemistry, and observe the energetic interplay of light and heat between a star and its planet. Contemplating these phenomena as you prepare for sleep allows you to visualize the gentle dance of clouds, the quiet currents of wind, and the slow shifts in temperature. Together, these elements create a sense of harmony and tranquility that soothes the mind and readies it for deep, relaxing slumber. The sheer diversity of these alien worlds truly staggers the imagination, with each newly found planet representing a distinct universe within our own galaxy. There are super-Earths, which are planets larger than our own but considerably smaller than gas giants. Their surfaces could be solid rock, possibly featuring oceans and atmospheres capable of maintaining a stable climate. You might picture their calm, expansive plains, a soft wind rustling through alien grasses, and distant mountain ranges that frame the slow, meandering courses of rivers. Then, there are mini Neptunes, worlds slightly bigger than Earth with thick atmospheres of hydrogen and helium. On mini Neptunes, the clouds might be dense and iridescent, forming slow-moving majestic vortices, while any solid surface remains concealed beneath the thick gaseous shell. You can imagine the soft luminescence of these clouds and the quiet whisper of winds, as starlight filters through the atmosphere like a gentle nightlight in a far-off home. We have also found hot Jupiters, which are gas giants orbiting extremely close to their stars, heating their atmospheres to scorching temperatures. On these worlds, winds can reach phenomenal speeds, while clouds composed of metals and silicates form strange bands and swirling patterns. Yet even in such extreme conditions, you can envision the quiet rhythm of their orbits and the smooth flow of gases shimmering in starlight, evoking a sense of incredible harmony. Equally mesmerizing are the ice giants, planets situated far from their star with frigid atmospheres rich in methane and ammonia, where water exists only as solid ice or frozen oceans hidden beneath thick clouds. Picture the soft radiance of these remote worlds, the quiet gleam of their icy clouds, and the slow, peaceful eddies that instill a feeling of eternal calm. A perfect soundscape for nighttime reflection. Each category of exoplanet unlocks new avenues for your imagination and for meditation, serving as another reminder of how wonderfully diverse and beautiful the cosmos is. By envisioning these worlds, you can connect with the peace of space, the gentle glimmer of distant stars, and the smooth breath of invisible winds, easing your way into a deep and soothing sleep. Imagine a super-Earth turning slowly on its axis, its shimmering oceans reflecting the light of a parent star. Picture a mini Neptune, shrouded in dense, softly glowing clouds that catch the faint starlight. You might envision a hot Jupiter, its swirling vortices and atmospheric bands unfolding like a magnificent, slow-motion painting. Or perhaps an ice giant, concealing its mysteries beneath thick cloud layers that suggest an infinite depth, reminding us that the universe is both boundless and wonderfully complex. Every planet, no matter its size or composition, possesses its own distinct atmosphere, climate, and patterns of movement. As you contemplate these worlds before drifting to sleep, you can connect with the harmony of the cosmos. Feel the steady, peaceful rhythm of these planets. See the gentle glimmer of distant suns, and let a sense of profound tranquility guide you into a deep and restful slumber. Worlds capable of supporting life have always captured the human imagination, as we instinctively search for the familiar within the vastness of space. As you relax, think about the quiet glimmer of faraway stars, the silent spin of planets orbiting their suns, and the slow, cosmic breath of a universe filled with limitless possibilities. Scientists focus their search on exoplanets within the habitable zone, a region where temperatures are just right for liquid water, the fundamental component for life as we understand it, to persist on a planet's surface. The precise location of this habitable zone shifts depending on the star. For cool red dwarfs, it lies much closer, while for brilliant hot stars, it is situated much farther out. Allow yourself to picture such a world, where a gentle morning sun just crests the horizon, casting a slow-moving stream of light that gradually warms its oceans and plains. Often, the most promising candidates for life are called super-Earths, worlds slightly larger than our own with sufficient gravity to hold on to a substantial atmosphere. It's possible their surfaces are adorned with vast oceans, sprawling continents, or polar ice caps, while their atmospheres, perhaps a mix of nitrogen, oxygen, and other gases, could foster a stable climate. Imagine the soft lapping of ocean waves stirred by a light breeze, the faint rustle of clouds overhead, and the delicate reflection of starlight on the water. This imagery evokes a feeling of deep peace and cosmic balance. To find clues of life, scientists analyze the atmospheres of exoplanets using a technique called spectroscopy, hunting for biosignatures, which are the chemical fingerprints life might leave behind. These telltale signs include elements and compounds like oxygen, ozone, methane, and water. Your imagination can help you visualize these unseen atmospheric processes, the gentle play of light and gas, and the quiet vibration of molecules in a delicate cosmic dance that travels across millions of kilometers before our instruments can perceive its music. While some of these potential worlds are relatively close, only a few dozen light-years away, others exist at incredible distances, requiring thousands of years for their light to reach us. Thinking of this before sleep, you can sense the unhurried passage of time carrying signals from these remote systems. These faint messages gently and softly convey the stories of distant planets, their oceans, clouds, and quiet winds, as if the cosmos itself is whispering its secrets directly to you. These habitable exoplanets serve as powerful symbols of hope and discovery, acting as a constant reminder that the universe is teeming with potential. They help us appreciate the uniqueness of every world, where each gust of wind and every veil of cloud is a note in the grand harmonious symphony of the cosmos. By picturing this as you fall asleep, you can immerse yourself in the peace, majesty, and boundless beauty of the universe, gently sinking into a deep and restorative slumber. The orbits of exoplanets are invisible tracks that guide these worlds on their journeys around their stars. Some are nearly circular, which fosters stable climatic conditions, while others are more elongated, leading to fluctuating temperatures and dramatic seasonal shifts, much like the gentle rhythm of a planet inhaling and exhaling. As you settle into rest, visualize the slow, graceful rotation of a world around a distant sun, a seamless motion that has persisted for millions of years, generating perfect harmony and stability. Many exoplanets revolve around their stars at extraordinary speeds. Worlds like hot Jupiter's orbit so closely that they complete a full circuit in a matter of days, which results in rapidly shifting weather patterns. Imagine their atmospheres in a state of constant, slow shimmer, with clouds rearranging themselves and gentle winds distributing heat across their surfaces, forming vast and silent vortices. In contrast, other planets, located much farther from their stars, exhibit slow, almost deliberate rotations that can span hundreds or even thousands of Earth days, creating steady climates where change occurs with a gradual, calming rhythm. Exoplanets frequently exist within planetary systems, where multiple worlds orbit a central star and influence each other through gravity. These gravitational tugs can lead to shifts in orbits, changes in axial tilt, and even dramatic swings in temperature, all part of a dynamic and harmonious interplay. You can picture these worlds in a soft and gentle cosmic ballet, slowly dancing with one another, as each celestial body finds its perfect place within the grand orbital architecture. Certain orbits are tilted in such a way that the planet receives varying amounts of light across different latitudes, giving rise to a rich diversity of climate zones. In your mind's eye, this might appear as sunlight moving slowly across the surface, enveloping one part of a plane in soft shadow, while another is bathed in warm, gentle light, instilling a sense of infinite calm and tranquility. Understanding exoplanetary orbits reveals not just climatic characteristics, but also a world's potential to harbor life. The slow spin of a stable orbit, combined with gentle interactions with its star and sister planets, establishes the necessary conditions for oceans, stable atmospheres, and the complex biochemical processes of life to emerge. By contemplating this as you fall asleep, you can feel the universe's inherent harmony, the majesty of these slowly moving worlds, and the quiet beauty that surrounds us in the infinitude of space and time. Consider the soft radiance of a faraway star, as its warmth slowly makes its way to a planet's surface, a delicate cosmic breath that settles over every stone, drop of water, and wisp of cloud. The star's radiation is a decisive influence, as the light and heat it sends out dictate the planet's temperature, the patterns of its atmosphere, and even its chemical reactions. Worlds positioned near their stars are inundated with tremendous energy, resulting in scorching surfaces and atmospheres that are both turbulent and dynamic. Imagine the gentle motion of clouds bathed in a luminous orange light, a slow-motion dance of matter and energy that has unfolded over millions of years. The gravitational influence of the star also generates powerful tidal forces that can alter a planet's environment. These forces have the power to slow a planet's spin, generate heat in its core, and exert control over its oceans and atmosphere, creating a silent symphony of movement as warmth rises from within. Many exoplanets possess magnetic fields that serve as a crucial defense, shielding their atmospheres from the erosive power of the stellar wind, a constant stream of charged particles. These magnetic shields manifest as a soft glow in the planet's upper latitudes, similar to the auroras on Earth. You can picture them shimmering gently in the darkness, inspiring a feeling of both magnificence and deep calm as they dance across the sky. The planet's relationship with its star can also govern its climatic cycles over long periods. For instance, subtle shifts in the planet's orbit and the tilt of its axis cause seasonal variations, which in turn gently control temperature and rainfall. This ongoing interaction creates a profound harmony that has persisted for eons, ensuring the stability required for life to potentially emerge and thrive. By examining these complex interactions, scientists can better determine which exoplanets might be habitable. They search for worlds where the atmosphere is stable, the oceans can remain liquid, and the climate is temperate and calm. As you think about this before falling asleep, you can connect with the harmony of the cosmos, the sheer scale of these invisible forces, and the quiet breathing of distant worlds that fills the universe, inviting a sense of profound peace, perfect for deep sleep. A magnetosphere is an unseen barrier that encircles a planet, protecting its atmosphere from the harsh conditions of space. Envision the faint glow of this shield, a subtle aura surrounded by quiet eddies of energy that flow smoothly into the void, forging a harmony between the planet and its solar system. On worlds with powerful magnetic fields, the atmosphere is held in place, preventing water vapor and essential compounds from being stripped away. This atmospheric stability is vital for the possibility of life, as it enables the formation of distinct climate zones and vast oceans. Picture how serenely the air currents circulate and how clouds drift slowly across the surface, reflecting the light of their distant sun and inspiring a feeling of tranquility. These magnetic fields also fend off cosmic radiation, which consists of particle streams capable of breaking down chemical bonds and harming biological molecules. On Earth, our magnetosphere produces the northern and southern lights, a soft, mesmerizing glow that captivates and calms us. You can imagine how on other worlds, this light show might appear in different colors and intensities, pulsing gently, like a slow, silent dance in the darkness that has continued for ages. A strong magnetic field is a key sign that a planet can safeguard its oceans, hold on to its gases, and support the chemical processes that could lead to biosignatures, the telltale markers of life. It is possible that some exoplanets have magnetic fields weaker than our own, which would leave their atmospheres more exposed. However, even these worlds could potentially hold on to clouds, polar ice caps, and oceans for millions of years. Imagine the unhurried flow of water, the gentle drift of clouds, and the quiet winds, all contributing to a sense of the planet's slow and harmonious rhythm, as if the universe itself were nurturing its creations. The universe is also filled with worlds that defy imagination with their hostile conditions. Picture a planet where the temperature soars to thousands of degrees, leaving the surface perpetually scorched and the atmosphere in a state of constant, violent motion. These are the hot giants, planets that orbit incredibly close to their stars and are saturated with immense amounts of energy, their swirling clouds shimmering in a spectacle of grand cosmic harmony. Elsewhere, you might find super-Earths, planets that are significantly larger and more massive than our own. Their gravitational pull is much stronger, and their atmospheres are far denser, causing processes to unfold at a majestically slow pace. On such worlds, you can visualize clouds drifting with immense deliberation and oceans moving under incredible pressure, creating quiet, powerful movements that feel eternal. Finally, there are the ice worlds, where temperatures plummet to hundreds of degrees below zero. On these frozen planets, vast oceans may lie hidden beneath incredibly thick sheets of ice, while their atmospheres are often thin to the point of being almost non-existent. Each of these different worlds tells a unique story of planetary evolution, shaped by the cosmic forces that surround it. Picture an almost complete silence, a place where icy plains stretch to the horizon, shimmering faintly in the glow of a remote star. In this realm, sounds are frozen in time, the winds are but a whisper, and the planet appears to be locked in a perpetual, unhurried slumber. Yet even in such extreme environments, the universe finds its equilibrium. On fiery giant planets, rapid atmospheric currents establish consistent cycles, while on super-Earths, stable and slow-moving climate zones take shape. On frozen worlds, the serene and unchanging icy surfaces preserve chemical elements in a state of stability. Contemplate the gentle, placid flow of these phenomena, as if the cosmos itself is orchestrating a perfect balance, permitting each planet to exist and evolve at its own distinct rhythm. These extreme worlds teach you to appreciate the universe in its full diversity and splendor. Every world is one of a kind, and an astonishing harmony reveals itself even under the most severe conditions. Holding this image in your mind before drifting off to sleep can help you feel the magnificence of the cosmos, the soft breath of planets, their gradual rotation, and their quiet communion with the surrounding universe, cultivating a sense of tranquility, peace, and majesty that is ideal for a profound rest. The search for exoplanets represents an incredible synthesis of science, technology, and patience, much like a slow journey along the unseen pathways of faraway worlds. Envision astronomers at their telescopes, gazing at the soft light of stars, hunting for the most minuscule fluctuations that could signal the existence of a planet. One of the most prominent techniques is the transit method, where a planet's passage in front of its star causes a slight dimming of its light. It's as though the star is momentarily cloaked by a delicate veil, a change we can detect from Earth. Visualize this sequence. The star emits a gentle glow, the planet makes its slow transit across its face, and our sensors capture these barely perceptible shifts, the faint whisper of a distant world that we have learned to hear. Another approach is the radial velocity method, which relies on the fact that a planet's gravity makes its star wobble ever so slightly. These minute oscillations can be measured with instruments called spectroscopes, which unlock the secrets of the planet's orbit. Imagine the star trembling gently, as if performing a silent dance to an unheard melody, while scientists back on Earth document this cosmic choreography, thereby confirming the presence of an unseen world. There are also direct observation techniques, where researchers use specialized filters and powerful telescopes to attempt to capture the planet's own faint light, distinct from the overwhelming glare of its star. This demands extraordinary precision and focus, but the potential reward, the chance to see a distant world almost directly, is immeasurable. Just think of a planet's soft luminescence in the cold void of space, its silhouette framed against a remote star. A quiet presence you can almost feel. Modern observatories, like the James Webb Space Telescope, give us the power to study planets across vast distances, analyze their atmospheres, and even search for signs of water and other essential chemical compounds. These sophisticated tools allow us to listen to the quiet murmur of the cosmos, slowly unveiling new worlds, much like turning the pages of a grand, deliberate book of the universe. Every method of observation demands patience, accuracy, and keen attention, and each new discovery brings you closer to comprehending the sheer diversity of creation. As you imagine the quiet night sky, the gentle light of a telescope, and the slow progression of data on a screen, you can feel the connection between humanity and these distant planets, fostering a sense of peace, calm, and harmony that is perfectly suited for sleep. A planet's atmosphere is its unseen cloak, a gaseous layer that gently swathes its surface, shaping unique conditions for its climate, chemistry, and the potential for life. Imagine the soft exhalation of gases as they move with a smooth, quiet, and harmonious flow, as if the universe itself were tending to the balance on every world. On exoplanets, atmospheres can be incredibly varied. Some are composed primarily of hydrogen and helium, light gases that form soft, nearly transparent clouds. Others are denser, containing carbon dioxide, methane, and water vapor, which create dynamic living layers where chemical reactions are constantly unfolding. Picture these gases slowly intermingling, producing subtle gradients of color, gentle sheens of light, and quiet motions that are invisible to the eye but can be vividly imagined. Scientists investigate the atmospheres of exoplanets through spectroscopy, which involves recording the subtle changes in starlight as it filters through the gaseous envelope. This data enables us to ascertain the chemical makeup, identify the presence of clouds, and even find hints of water, one of the vital indicators that a planet could support life. Visualize the soft glow of spectra displayed on a monitor, appearing like distant lights that narrate the story of these invisible realms. The clouds on exoplanets are equally diverse, potentially formed from water vapor, ammonia, sulfur compounds, or even metallic elements. These clouds drift slowly, creating atmospheric patterns that have followed their own rhythms for millions of years. Imagine their gentle, swaying motion and their soft shimmer against a far-off star, a quiet and majestic dance that can neither be rushed nor halted. Some planets exhibit signs of chemical compounds that, on our own world, we associate with living processes: oxygen, ozone, and methane. The discovery of these biosignatures gives scientists a glimmer of hope that, somewhere else in the universe, organisms might thrive. Imagine how these molecules gently combine in an atmosphere, generating an invisible rhythm of life that you can only picture, but which fills you with a sense of wonder and tranquility. The atmosphere serves as a bridge between the planet and the cosmos. It is soft and yielding, yet immensely powerful and grand. By imagining its slow movements and quiet respiration, you can sense the harmony of an exoplanet, its gentle relationship with a distant star, and the unseen forces of the cosmos. This feeling of calm, serenity, and boundless majesty is ideal for a deep and restorative sleep, allowing you to dissolve, for a moment, into the gentle breath of distant worlds. When we think of life on exoplanets, we are envisioning not just chemistry, but the delicate equilibrium of conditions that allows those reactions to persist for millions and even billions of years. Envision a world turning leisurely on its axis around its star, its atmosphere softly diffusing the light as oceans murmur quietly beneath the gentle radiance of a remote sun, all coalescing into a perfectly balanced space. To identify potential life, astronomers emphasize the importance of the habitable zone, that specific orbital region where the temperature permits water to persist as a liquid. This area is neither excessively hot nor bitterly cold, representing an ideal point of equilibrium. Picture the delicate light from a star just gracing the planet's surface, providing enough warmth to ensure oceans do not turn to ice or boil away into vapor. This gentle, steady rhythm creates an environment perfectly suited for life to emerge. The habitable zone, however, is not the sole requirement. The atmosphere, magnetic field, chemical makeup, and orbital consistency are all equally vital components. An atmosphere is crucial for trapping heat and shielding the surface from cosmic radiation, while the magnetic field acts as an invisible protective barrier. The right chemical composition enables the formation of organic molecules, the building blocks of life, and a stable orbit is necessary to prevent drastic and destructive climate shifts. Imagine how these elements subtly work in concert: unseen forces, remote stars, and currents of gas all moving in unison to foster the conditions for life that, at this moment, remains only a possibility. Some exoplanets orbit far too near their stars, turning them into scorching giants with chaotic atmospheres, where any water would instantly vaporize. Others are frozen worlds found at the fringes of their systems, where water is locked into immense permanent oceans of ice. Yet it's conceivable that even in such forbidding environments, microorganisms or other life forms uniquely adapted to these strange conditions could thrive. You can almost feel the slow progression of these processes, the unhurried creep of ice, the silent shimmering of gases, where life might still carve out an existence. Contemplating habitable zones and the various factors that support life allows you to undertake a mental voyage across the cosmos, envisioning millions of worlds, each with its own distinct harmony and tempo. These imaginative journeys gently occupy your thoughts, fostering a feeling of calm, wonder, and cosmic unity. They seem to lull you slowly, drawing you into a peaceful slumber where you can drift weightlessly among the distant stars, oceans, and clouds of alien planets, sensing that every world pulses with its own serene, quiet, and majestic rhythm. Exploring exoplanets is more than just analyzing data or observing distant stars. It is a meditative expedition into the universe's depths that lets you see reality through the eyes of the cosmos itself. Picture yourself standing on the edge of our world while your mind soars among countless star systems, each one safeguarding its own secrets and splendor. In this gentle voyage, our guides are the telescopes and space missions that reveal what is imperceptible to the unaided eye. The unhurried rotation of planets, the clouds drifting over distant worlds, and the quiet cadence of their atmospheres. Through these instruments, you learn about blistering gas giants, frozen ice worlds, and massive super-Earths, gaining insights into the chemical makeup of their atmospheres and the prospects for life. Imagine how the data from telescopes gradually assembles into a complete portrait of the universe, much like a slow melody that both soothes and fascinates. Examining these other worlds deepens your understanding of Earth's own uniqueness, its delicate atmosphere, its abundant water, its vibrant biosphere, and the sheer magic of existence. Every exoplanet discovered serves as a mirror, reflecting our own planet's vulnerability and magnificence, and inspiring a greater appreciation for the extraordinary equilibrium that has permitted life here to flourish over billions of years. As you visualize the soft glow of an earthly sunset, you can simultaneously imagine the glimmer of faraway star systems, a harmony that evokes a profound sense of peace and reverence. The dream of journeying to other planets and stars is not mere fantasy. It reflects humanity's deep-seated drive to broaden its horizons and comprehend its place in the universe. Even though we may never physically set foot on most of these worlds, our imagination and scientific inquiry allow us to glide among them, studying their rhythms, atmospheres, and concealed beauty. Each planet you learn about becomes a new chapter in the endless saga of the cosmos, gently unfurling before your mind's eye. In a philosophical sense, the study of planets and exoplanets imparts lessons in humility, patience, and harmony, as you come to grasp the universe's immense scale, diversity, and breathtaking beauty. As this exploration concludes, picture yourself floating serenely among planets and stars, feeling the gentle drift of clouds on distant exoplanets, the quiet lapping of their oceans, and the slow pulse of their atmospheres. Let this gentle cosmic lullaby fill your mind with peace and tranquility, allowing your body and consciousness to descend into a deep, restorative sleep, where dreams of the cosmos become an integral part of your inner world.